Good morning, good afternoon, and good evening. Welcome to this presentation on the Hyperonomy Universal Decentralized Identifier URI specification. My name is Michael Herman. I live on a ranch in southern Alberta, and our snow has now left us, and so it's a little bit of a mess out there. So just a note here, because it's kind of late breaking news. The did-uri-spec has been renamed everywhere to be the did-uri-spec. This was creating a lot of confusion, calling it did-URL. Where it came from is, if we look at the grammar here, this is the before Barcelona grammar, it had something called did-URL, and I kind of fixated on that. When I create the actual did-uri-spec grammar, that rule will be called did-uri. And so there shouldn't be any confusion about that. So even the project up on GitHub has been renamed. So everywhere. And then just kind of a footnote, and this is almost like the simplest summary of this whole presentation. A did-uri is an identifier, a unique specification for what type of document is to be returned. And there's many types, as shown on slides 45 and 46. We'll just quickly look at slide 46 because I want to continue with the rest of the deck scenarios. So here we've got about 19 currently. And so we see, for example, number one, a did is going to resolve to a did document. That's simple. In number two, we see the use of the select ID transformer. And for convenience, because we believe that did document fragments are probably going to resolve frequently or more frequently than anything else, we're also maintaining some backward compatibility with the # notation. Because we're continuing, it's not necessary, but one reason is we're continuing to use the # inside the did document. So, the did exclamation $select ID equals WXYZ, that gives us a fragment. Instead of using the select ID transformer, we could use the content ID transformer. In that case, we get a did document content fragment. Service ID, we've already talked about. There we don't get a did document and we don't get a fragment. We get a remapped service endpoint, URI or URL, depending on how service endpoints are defined. Often they'll be HTTP, sort of RESTful requests, or it could be a WS socket request. It could be whatever protocol that service endpoint understands. Attachments, we already talked about attachments. So this is being able to extract attachment ABCD out of an Indy 8-way agent-to-agent message. So this is a message attachment fragment. In the Indy feature discovery spec, there's the ability to query all of the service agent features or feature descriptions. So part of the JSON for the request object is the query attribute, and there you pass in the did URL that represents your query. So here we're saying for a particular did, we're going to pipe that through $filter this time. And the filter is star. It's a wildcard. So this says return everything to us. In number 7, we can see a similar construct, but when we look at the filter expression, it doesn't just say star. It says /tic-tac-toe/1.star. So this is only going to give us the tic-tac-toe features. So we call this an array of filtered service agent feature descriptions. Number 8, if we pass in a did method like did : foo : or did : solve colon, and we pipe that into dollar service capabilities, we're going to get an array of did method capabilities, all of the did method capabilities. We might be interested for a particular resolver or for a particular did method, in this case did colon xyz colon, and simply getting all of the documents. And you might say, yeah, there could be hundreds of thousands or millions. There's other constructs that we'll see a little bit later when we get into the detailed low-level use cases for controlling how many documents are returned, which documents are returned, essentially a batching type capability. But the important thing here is we get an array of documents. So if you do just a quick scan down the right, every one of these returns a different result. In the first page here, we've got 9 different types of results from DIDs. We're solving the elephant problem. The status of this specification, this is a work in progress community member contribution. So this is a frequently used diagram when it comes to describing sort of the specification process or the way that the community-based approach to developing protocols. So the current status or state of this specification is it's over on the left, figuratively that green bar. It's a proposal coming from a particular organization, the Hyperonomy project, and it's being presented or proposed as a community protocol, a broad community protocol for did URLs in every way that they're used. This is different from the did-spec effort. This is different from the did resolution effort. This is different from some of the Indy hype efforts, which are looking at individual protocols. And so the current intention is for this specification, the did-url-spec specification, to be merged into those other specifications, the W3C Decentralized Identifier draft community specification, the did resolution draft community specification, as well as other related specifications, and I've already highlighted the Indy hypes, either directly, it's having it merged directly by reference, or as an appendix for those specifications. So I encourage you to keep an open mind. As a standalone specification, as a standalone community member contribution, you're going to find that this deck, this presentation in particular, is fairly comprehensive. One of the concepts that permeates this project and the development of this specification is this concept of progressive improvement. And so on the left of this slide, you'll see kind of a 3-version approach. Make it work, and by make it work, I mean make it work by almost any means possible, make it work better, and make it work right. And so a lot of progressive improvement, subsequent refinement. This specification is a result of iterating from version 1 to version 2, iterating from the previous did ABNF examples that we had in the did-spec and that we've been working on in the did resolution community, to a point now where it's clear that the did URL grammar needs to be a standalone specification, leveraged not only by did-spec and did resolution, but the Indy hypes and any other specification that needs to reference or make use of distributed identifiers. You can read more about this concept of progressive improvement in my blog article entitled How We Think About How We Work. So the purpose of this specification is to document the development as well as the final version of the did URL grammar for the Decentralized Identifier URL specification, did-url-spec for short. The primary audience is implementers and maintainers of parser software that is compliant with this spec. And there's a broad range of software that can benefit from using this spec. A broad range of software any software that uses DIDs and needs to be able to parse and action on the understanding created through that parsing process. So we've already highlighted the W3C Decentralized Identifier specification, the DID resolutions specification, and as well as agent-to-agent communication servers in the Hyperledger Indy Agent framework. Goals and non-goals. So the two primary goals are to document the development of the spec version of the did URL grammar. Next, it's to publish the final version of the did URL grammar for this specification, for the did URL spec specification. Non-goals, it's not a goal of this discussion or this specification to force any particular project or existing specification effort to adopt this specification. But it is hoped that this specification will significantly influence the current state and all future states of the did URL grammar discussions. There's several levels of user scenarios and use case information. The driving force are any specification that mentions DIDs, because they potentially represent either low-level detailed use cases, but more likely they represent high-level use cases. In the case of the W3C Decentralized Identifier specification, there's a companion use case document, which again paints some high-level, what I call user scenarios. Did resolution is doing the same thing, as well as the Indy Hypes. Although the Indy Hypes tend to include a lot of specific, for example, JSON code that has embedded DIDs in them. So it's a combination of being higher level user scenarios and lower level did URL use cases. So this document is a specification, again, just to repeat myself a bit, specifically for the decentralized identifier URLs, as described by the did URL grammar, that is defined using the ABNF notation. For a better understanding of the terminology we're using here, grammar, notation, etc., I refer you to this article, Giving Grammars Written with ABNF Notation the Respect That They Deserve. And I think I'm going to show a screenshot of that fairly quickly, and you'll find that on my blog. So the motivation for creating the did URL specification comes from a February 21st did resolution community call, where there was an early discussion about using a particular HTTP binding, and here you see two examples of it, and in particular note the word resolve and the word dereference. And it seemed odd to me that you needed those words resolve and dereference, because if you actually look at the did URL, the portion of the HTTP URL that starts with did : it already indicates whether it's a resolution function or a dereferencing function. So a seemingly innocuous comment has kind of snowballed into what we have today. And at that time, the grammar, the did grammar, if you will, was referred to as the did ABNF, almost exclusively, kind of a nickname. It just seemed at odds. So if we look at the bottom three examples, kind of as a response to the two URLs at the top, we see resolution in this scenario. Why not just say simply http://uniresolver.io/ and the did for the document? Or in the simple dereferencing cases, there's two alternative syntaxes: HTTP //uni-resolver.io, the URL did:/xyz:1234, and then what we're doing is we're dereferencing off of key 1 and returning a did document fragment. In the spirit of being open for innovation, open for future innovation, we're also relying heavily on the last notation you see there within the did-uri-spec, uniresolver.io/did:/xyz:1234, and then exclamation mark $select ID equals key. Those are exactly identical to each other. They return the same did document fragment. And the idea is, from a syntax perspective, those dollar options, like select ID, just specifies a pattern. It's $identifier equals some value. Select ID doesn't become part of the syntax or part of the grammar, other than just being an option string. We'll see a lot more of that as we go. The other thing that's kind of characterized the different, did ABNF and did URL grammar discussions to date is every group, every committee tends to be looking, at their own part of the landscape through their own lens. And so I thought an interesting metaphor for this is the blind man and the elephant problem, where we have three blind men here. They're all touching and connecting with different parts of the elephant, and none of them can agree on what it is that they're looking at. So my intent is to be able to back up, let's look at the whole elephant, and try and come up with a specification specifically and only for did URLs. So it's really a specification for creating did URL parsers, so that can be a shared component, a reusable component across all of these different domains. And very shortly, I'm going to take you through those. So, here I've highlighted, there's the perspective of the did spec, the did resolution spec, RFC 3986 gets quoted at length. There's the did ABNF, there's naked dids, all kinds of terminology is being invented, and we need to go back, and this is where that article about grammars defined with the ABNF notation need to get the respect that they deserve, and again, I'm going to show a slide about that in a minute. So there's the did-ur grammar, which is the proper term. Did ABNF implies that there's somehow a did variation of the ABNF specification, that there's a different kind of ABNF, and that's just not the case. So, and then the Indy Hypes are looking at did URLs and the did URL grammar, from a different perspective, and it's hoped that this specification approach, focusing just on did URLs and the creation of did URL parsers, will help us see the entire elephant. From that grammar and specification document on the lower left, there's going to be a reference implementation of the did URL parser, and Java, C++, and C#, and that will be using the parse2.com parser that is already being used, for example, in the Universal Resolver framework. And that parser then will be applied to all of these corresponding application areas. A reference did resolver. In the Indy Agent framework, wherever dids are used or being referenced. Feature discovery, for example. More specifically, other aspects of the Indy agent-to-agent communications protocol, and on and on. I've tried to focus on the specific specifications, which I call the higher level user scenarios, driven by the existing documentation. There's still a lot more documentation to be digested. From that grammar and specification document, on the lower left, there's going to be a reference implementation of the did-URL parser, and Java, C++, and C#, and that will be using the parse2.com parser that is already being used, for example, in the Universal Resolver framework. And that parser then will be applied to all of these corresponding application areas. A reference did resolver. In the Indy Agent framework, wherever dids are used or being referenced. Feature discovery, for example. More specifically, other aspects of the Indy agent-to-agent communications protocol, and on and on. I've tried to focus on the specific specifications, which I call the higher level user scenarios, driven by the existing documentation. There's still a lot more documentation to be digested. Okay, so the approach is, if we look at the history of the did-spec, there's a lot of what I call original architectural principles, high-level concepts that were used to draft an initial version of the did ABNF, more properly called the did-URL grammar. And how do we take those high-level architectural principles to create what I call lower-level set of did-URL use cases? Actual did : strings that represent all the different options and alternatives. And so where do we get those? We get those by looking at the Indy hypes. We get those by looking at the use case documents and imagining what the URLs are that would support those higher level user scenarios. Step 2, we take those lower level did URL use cases and we use them to drive the design of the grammar, expressed initially at a high level using ABNF notation. We're kind of using what I call a pushing rope strategy currently, where we're designing the ABNF and imagining if it's the right ABNF or not based on the higher level use cases. We're missing the actual low level did URL use cases, the ones that you can actually run against a parser, automatically generated using the did URL grammar, and using the did URL use cases to drive the creation of the grammar and to drive the validation of the grammar. So in step 3, we're going to use the high-level design for the did URL grammar to drive the implementation, actually creating the ABNF source code for the actual did URL grammar. And then we're going to validate that did URL grammar by testing it using test cases based on each of the individual specific did URL use cases. And we're going to see lots of examples like that. But it's really a software development approach. It's really realizing that the ABNF source code, the ABNF notation for a did URL grammar is actually source code, and it's source code for an executable program. It's source code for an executable program that when it executes, it's able to read a string of tokens, i.e. a did : string. It's able to validate that that string is a valid string and take action on each of the parts. So the idea that the did URL grammar is actually a piece of source code written using ABNF notation that can be executed. And if it can be executed, then it can be tested just like any other program. And of course, we're going to iterate on that because, for example, at the beginning, we're not going to have each and every high-level did user scenario. We're going to focus on the, some main ones. But as we, for example, move and study more and more of the Indy hypes, we're going to find more and more variations of the did URL use cases that are needed to support those hypes. And as we've already found, there's times when we can provide feedback back to those Indy hypes, where, for example, the ID field, which is typically or optionally a did, in one hype was called nickname. And so there's an active discussion now whether that nickname attribute, whether the name of that nickname attribute, should actually be changed back to ID to be more consistent with the grammar and the parser and the processing side of it. Okay, I always believe in having a strong set of guiding principles, a strong initial set of guiding principles, even a weak set of initial principles that you can iterate on. And use those principles, have those principles in place so that it'll help you answer questions later on. Should we have done this or should we have done that? There should be a principle that will guide you. So two of the principles, what I call the core principles, are expressed in these following documents, and this is where I'm going to finally show you those documents. There's the open to innovation principle, that internet protocols and standards not only need to be open, but more importantly, they need to be open to innovation. Secondly, giving grammars written with ABNF notation the respect that they deserve. That is, treat them like programs, develop them like programs, have an iterative, agile software development process and testing and validation process, just as if it was a program. We need to make sure that application developers who are using these parsers directly or indirectly in all of these different application scenarios can, efficiently search, find, resolve, and dereference, single did documents that might be associated with the did, or perhaps a collection of did documents associated with, some filter criteria. And we're going to see many more types of outputs, not just single documents and collections of documents. Another sort of instance of number 2 is number 3, which is about being able to dereference a service endpoint and use that to remap the did URL into a URL that's compatible or address that is able to address the service endpoint and execute against it. So here's the Open to Innovation Principle blog article. It's a short one, 2 paragraphs. You can find this on hyperonomy.com, and it came to be just a few weeks ago when I was at the Hyperledger Indy Developer Bootcamp in Vancouver, and I was fortunate to overhear and participate in a conversation where Sam Curran, aka Telegram Sam, was talking to a small group of developers about the importance over the course of history for internet protocols not only to be open, but more importantly, to be open to innovation. And that includes innovations that might succeed as well as innovations that might fail. And more specifically, he talked about TCP/IP and TCP/IP packets. His quote here is, if you look at important internet protocols like TCP/IP that enable packets on a network to carry any type of data, including text, email messages, web pages, etc., and then later on streaming audio and streaming video, which has become very commonplace today. But back then, who could have imagined it? So it's vitally important for internet protocols not only to be open, but open to innovation. Innovations that might succeed as well as innovations that might fail. No one can foretell how the specifications we're creating today will be used in the future, and that is going to be a key principle, the open to innovation principle, that will permeate the development of the did URL grammar. The second article that contains core principles is about giving grammars written with ABNF notation the respect they deserve. At one level, augmented BNF or ABNF notation is simply a convenient textual way for describing a grammar, and that's how it's been used in the did-spec for the last few years. In turn, a grammar is a description of the allowable linguistic characteristics or constructs permitted in the language. in a particular language or any other sort of syntactic construction. So did URLs is just one example. Examples of common and emerging grammars written using ABNF notation, including, the URLs for the World Wide Web. If you go and find that reference, they use ABNF notation. The OASIS ISO Open Data, OData Open Data specification is defined fully using ABNF, and of course decentralized identifiers. So one of the driving specifications for this effort, which is the did-uri-spec. More importantly, a grammar that conforms to the ABNF specification, RFC 4234-4, is also an executable program. And this is, when we talk about giving ABNF notation the respect they deserve, grammars written with the notation the respect that they deserve, this is the key part. That these grammars are executable programs. That is, a grammar is the source code for a program written in the ABNF notation, aka the ABNF programming language, that creates programs that recognize and optionally process a piece of text, i.e. a string of tokens, that conforms to the grammar specification. And the grammar specification is that notation. So if we kind of summarize some of the principles here, specific related to grammars created with ABNF notation, in a way this is a bit of a glossary or a taxonomy. So ABNF is a specification for a notation for describing grammars. So earlier on, I criticized the use of the phrase did ABNF, because that would imply that it's a different kind of ABNF, and it's not. So ABNF is a specification for a notation for describing a grammar. ABNF notation is the notation described in the ABNF specification for describing a grammar. So it says how a grammar is supposed to look, how it's supposed to appear, how it's supposed to be constructed syntactically and semantically to have meaning. A grammar, in turn, is a description of the allowable linguistic constructs permitted in a particular language, the language being described by the grammar, or any other syntactic construction. RFC 4234 is the formal specification for the ABNF notation. A grammar expressed with ABNF notation is intended to be executable. In fact, www.parse2.com is an online resource for automatically taking these grammars expressed using ABNF notation and making them executable. Generating code that makes them executable. A grammar expressed using ABNF notation is the source code for a program that can be read, interpreted, compiled, or executed by a human, an interpreter, a compiler, or a virtual machine, respectively, in a way that conforms to the ABNF formal specification. When we think of the www.parse2.com site, it in effect is a transcompiler in the sense that it takes a grammar written in ABNF notation and transcompiles it or translates it into Java, C++, or C#. And then from there, it can be interpreted, compiled, or executed. So some best practices for developing grammars. Once you've given them the respect that they deserve, what are the best practices for developing grammars written using ABNF notation? As in any software development project, it is of primary importance to understand the scope of the functionality to be delivered, the inputs and outputs, for the intended software, aka the requirements for the software functionality to be created. One of the best commonly accepted ways to understand the scope of an intended piece of software to be developed is to work through a series of artifacts, starting with higher level, user stories, which in turn are decomposed into scenarios and use cases, requirements and specifications. And when we looked at the approach earlier on, this is exactly what we're advocating. Use automation together with the use cases to create an automatable testing framework starting early in the project, automatically validating the grammar against the use cases. So use cases and test cases come first. Validate the grammar after you have those use cases and test cases, not the other way around. These artifacts can be developed, iteratively using an agile or any other type of development framework. It doesn't have to be doesn't require a waterfall approach. Okay, the last page of guiding principles. To ensure that all of the above operations and capabilities are expressed in a consistent, did URL syntax, eliminating the need for creating additional language or API constructs whenever possible. So you think of those first two examples, those first two URLs where it had the word resolve and the word dereference in there, just totally extraneous and it doesn't need to be there. We don't need to create a bunch of extra language or a different language to wrap the did URL grammar if the did URL grammar is already capable of expressing it. That isn't to say that there aren't some operations that might need, optional values or optional parameters. And you shouldn't try to just jam everything into the did URL, but where the did URL naturally specifies what is to be returned, not how, but what is to be returned, it should be encoded in the did URL grammar. 5 is getting a little bit dated, but it's really saying that whatever this grammar is that we put in the did spec, from a syntax perspective, from a syntax specification perspective, make sure that it doesn't unnecessarily restrict innovation with respect to how did URLs are parsed. If you remember that earlier example where the did URL, where the did was piped using the exclamation mark into $select ID equals foo. That's an example where we are supporting in a properly defined way the ability to support future innovation. You might have $select ID, $content ID, $service ID, but the syntax, the grammar, should only say that there's $ followed by some name. And it's up to the subsequent semantic analysis that is applied, to the parse structure that gives meaning to those. It shouldn't be a restriction within the grammar. Ensure that the application developer has the tools he or she needs and has the basic operations, to test if a did resolver is alive and responsive. So this is a little bit about management and control of the did resolver, and not just simply the simplest plain did, dids that resolve to did document type scenarios, and we'll see some examples of that. The lower level did URL use cases will be guided, aka driven sometimes, by the specific higher level did user scenarios. And I use the word guided here because they are higher level did user scenarios, what we find in most of the specification documents, what we find in most of the current use case documents. They're higher level scenarios. And we're combining those scenarios across many specifications, many application domains. So collectively, should maybe put the word collectively guided and driven by those use cases. And of course, we're going to be compliant with 3986, which is the Uniform Resource Identifier syntax specification. Again, this 3986 highlights that it's a syntax specification, which is what we're trying to support. Okay, the people that are watching this probably have quite a varied background when it comes to compiler construction and parsing and query engines and all the things that are related to the field of endeavor here. So I'm going to go into that background a little bit And my apologies for those that are already familiar with these principles. Okay, so kind of jumping in a little bit deep here, we're talking about, an optimizer. So we're going to parse something. We're going to do some semantic analysis to understand what that something is. And then when we look at how that something is represented in a particular data store, we probably need an optimizer there. Something that understands what we're trying to do and how the underlying data store is physically organized. I didn't mean to go into optimization so much, but I'm really keying in on these statements, like the one in the blue, or excuse me, in the green rectangle. And I'm going to start using, SQL Server query language as an example, and I'm going to use others like the Cipher graph database query language as well. So T-SQL, when you look at it, we're going to see an example, I think, right away, defines what is to be returned, not how. And when you look at it, when you see select and group by and order by, you kind of assume that it's describing how things are supposed to be done. It doesn't. What it's describing is what is to be returned. And so in effect, those are logical requests against the data store, in this case, the SQL Server relational database. And the purpose of the optimizer, the SQL optimizer, is to take those logical requests and map them into efficient physical requests, physical plans, actual sequences of operations that will be executed against the data store. At this point, we're into the how, but it's up to the job of the semantic analysis and the optimizer and the execution engine to bridge from the what to the how. So the key thing is T-SQL is a declarative language. It's not a functional language. The Cipher graph language, which we'll see a little bit some examples of, is the same thing. It's a declarative language. The same thing applies to did-URLs. Did-URLs don't tell us or tell the resolver how to do anything, how to do things. It's just defining what needs to be returned. So here's a SQL example. Again, people look at that and say, well, it's telling me how. It isn't. It's telling me what. It's telling me what to combine. It's telling me what fields to join. It's telling me what keys the result output is to be sorted or ordered by. So T-SQL, just to repeat a bit, is a declarative language. It describes what is to be returned. It's not a functional language. It doesn't describe how to access or how to enumerate over the data store. And here's what's called the clause ordering, the SQL Server clause ordering. That ordering is declarative. It's not functional. It says to process these in order, but this is processing things in order from a what perspective. It's up again to the semantic analysis, the optimizer, and the execution engine to actually bridge from the what to the how. So, here's my example. T-SQL, it's parsed, runs through an analyzer, runs through an optimizer, specifically for the particular relational database store, and then the execution engine, which runs the actual physical plan against the physical database. Here's Cipher. Cipher is the, I believe it's approaching international standardization from a status perspective, but it's the native language understood by the Neo4j graph database. But as we'll see on a specific slide for Cipher, it follows the same model almost exactly. NoSQL databases, same thing. Parse, analyze, optimize, execute. So just looking at that pipeline in a little more detail and giving some names to the different phases of the process. So number 2 on the lower left-hand corner, that's the parser, and it undertakes the parsing process. And if we look at Cipher statements or we look at did-URLs, there's a parser that generates an abstract syntax tree. And then there's an algebraicizer, which is the analyzer. And I lump all of these last actions or last activities into processing. So we talk about parsing and we talk about processing. Within processing, it breaks out to semantic analysis, optimization, and execution. And we see that optimization is taking some statistics, some past history information about the execution of the execution engine. It may actually store a bunch of recently or frequently used queries so that their results can be executed and returned immediately. You know, there's lots of stuff going on here. Also, coming out of the semantic analysis is a common phrase: hard parses and soft parses. So for example, let's say the did URL that you're processing is did:ABC:1234. Well, we know that that particular pattern always returns a complete did document. It never does dereferencing. It never does anything special with service endpoints. So that's called a soft parse. And so we can take that, we can recognize that scenario and pass it directly to the execution engine. When we start using a bunch of exclamation, $filter, $select ID, etc., then we have a more complex AST, abstract syntax tree. And so we have to perform the algebraicizer analysis on that tree to figure out exactly what is being asked of the execution engine. And then depending on how sophisticated the implementation is of your, let's say, your did resolver, you may or may not have an optimizer. But if you're talking about competitive market pressures, as soon as some platforms start to come up with optimizers specifically for their platform, and they run a heck of a lot faster than the next did resolver, you'll see activity there. This is just some more slides talking about that parse, optimize, execute, processing stage. That previous one might have been a NoSQL. This is another way that Microsoft describes the SQL Server processes of parse, algebraicize, query optimizer, query execution, again to pursue a result. And at the top you see sort of the main data structures that are passed along. So there's the initial parse tree or initial AST, then there's the algebraicized tree, which is the abstract syntax tree, and it might have special markers or annotations added to the tree. And then out of the optimizer, we get an execution plan that is finally executed against the store. This is just re-emphasizing on its own slide the concept of soft parse versus hard parse. So a soft parse is when a did URL is composed of a did only, with no additional grammar rules or features specified, and only physical access optimizations are possible at the very bottom here. A hard parse is when a did URL is composed of a did plus additional grammar rules, or aka features, such as $exist, $select ID, etc. So again, we have this ability to shortcut when it's a soft parse, and a more laborious route doing interpretation, optimization, and more sophisticated execution. Let's talk about execution plans. So here's a SQL Server example. This is SQL Server Management Studio. In the top green box there, you can see a select statement, and it's taking the human resources employee table and EA, I guess it's joining it with itself, and with the person table. It's joining it with the person table, and it doesn't matter so much where what the specific select statement is, but this shows the execution plan. This shows how the how in the green box at the top gets translated into, excuse me, the what in the green box at the top gets translated into an executable plan, a how at the bottom. Here's a Neo4j example. So we have a cipher query, an innocuous looking cipher query. On the right, you see the query plan. So this is what comes out of the optimizer, and we're not going to look at the details, but it looks like a complex execution plan. It's highly optimized. In some cases, there's more optimizations are possible, potentially by recoding your query, but you get a visualization here of how all the different kinds of data is fetched, how much data is fetched, and how it's combined and recombined. So that's an interesting example. Here, in the case of Neo4j and Cypher, here's what their parsing and processing pipeline looks like. So the query text becomes an abstract syntax tree, semantics analysis, we get a typed AST. Planning is what they call their task or their process for optimization. Create a logical plan and then a physical plan, and finally we execute to get the results. So that's the end of the background, the generic, parsing and processing. Should have brought everybody up to speed now, and we can talk more specifically about did-URL parsing and processing. Okay, so I'm just going to bring these back. Remember, these are the non-did-URL scenarios: parse, analyze, optimize, execute against the respective store. And we saw this before, and we're being reminded that languages, the role of a language is to specify what and not necessarily how. That we're actually creating or writing logical requests, and that these languages, including the did-uri-spec, are declarative languages and not functional languages. So here's the did-URL example. So this is the one that the did-spec talks about the most. This is the one that the did-resolution-spec talks about the most. But there's quite a significantly greater number. So for example, there's the feature discovery hype on the Hyperledger Indy platform, part of the agent framework. And so you have the ability with feature discovery for one agent to ask another agent, what are your capabilities? And the way that you specify that is using a did-URL, and we'll see an example of that. So, the optimizer is for the agent functional database, and the execution agent is for the, agent functional database. And we can see that it's the same pattern all over again. Here, did-URLs are being parsed. Again, this is an Indy hype scenario, and what we're doing is we're retrieving message attachments within the agent-to-agent communication protocol. Lastly, there's did-URLs that are simply the value of an ID attribute within a piece of JSON, for example, on the inside of a did document. So that's another user scenario. And the reason why I highlight this is because the syntax we use for the ID attribute, a lot of the current thinking says that it has to be different based on how it's being used. That if it's an ID attribute, let's say for a service ID, maybe it should be using a semicolon. Or if it's a ID attribute for just a more generic or arbitrary, fragment of the did document, maybe it should be using £. The thesis here is that you should just be using £, all the time when you're talking about the ID value of an attribute. And the semantics is actually implied by the query, by the did-URL you're running against it, and we'll see some examples. In the very most recent March did resolution community call, there was an interesting discussion where dereferencing of a did URL was described as a process that starts with or requires the resolution of a did document. The did document that's associated with the did URL, and then continues to dereference whatever the fragment is or service endpoint is against that did document that returned as an intermediate result. While this may be true at a very conceptual level, at that high kind of architectural level, conceptual architectural level, and it may be applicable for some did methods and their corresponding verifiable data registries. As a generalization, it's not true, and it shouldn't be used or described, because it really throws people off when they hear that to do a dereference, you need to return the did document. It all depends on how your verifiable data registry is designed. In the case of Indy, you have separate transactions for NIMs and attributes. So there's times when you just need the NIM. You don't need to recreate the entire did document. So this is just highlighting that conversation, how when we're loose with these kind of conceptual terms, it can really lead us down the wrong path. Going down to the third bullet there, did URLs are expressions similar to any expression sent through a parsing and processing pipeline. So we're trying to say that it really isn't any different. It's syntactically it looks different, but conceptually it's not any different than any other query sent against a data store. And that these are logical expressions describing what is to be returned. So whatever the expression is, whatever the did URL is, it needs to be passed, down through the layers, and at the appropriate layer before you get to the data store, the software is going to say, oh, I know what this is, and process it accordingly. So the form, function, intention of a did URL is to describe what is to be returned, not how it is to be returned. So let's look at an example, and we're going to use it from category H. And category H introduces the concept of the exclamation point transformer option. And we've seen a little bit of this so far, and in particular, we're going to use the service ID transform option. This example, this illustration, also parallels very much Phil Woodley's article, and we're going to refer to that in the next couple slides. So the general process is you take all the tokens that immediately precede, the exclamation, and this should be formally the text that matches the did rule, the first rule of the BNF. And the semantics are take the did text up to the did pipe and pass it through a transformation represented by the transformation options that follow to the right of the pipe transformation option. So for example, if the transformer is service ID equals, and then quotes some service ID, the effect is to produce the resolved URL for the service endpoint corresponding to the service ID. So conceptually, we take the did, we pipe it, and to apply a transform based on the transfer options, and we produce a transformed URL. This will become more clear on the next slide.
This is a sample did doc, one of 3 or 4 that are part of the did-uri-spec project. This one is from Phil Woodley's blog. You see the URL at the bottom, and we're going to use it in the next couple examples. There's the one ID attribute that's kind of highlighted in a golden color, and that particular did URI we're going to use as a sample. We look at an example. So Phil Windley has an article which I guess I haven't got the URL for, but we'll add it to the slide.
and they make clear the difference. So we have two sets of examples here. So the first example uses Phil uses did colon SOV colon 1 2 3 4 up to J semicolon exam underscore SVC. So this is dereferencing the exam SVC service endpoint. Exam underscore SVC is the service ID. Using transformer notation instead, we would take that did underscore or did colon solve colon 1 2 3 up to J, and there's the pipe symbol. And here we're saying we're going to pipe it. We're going to transform either that did or the did document that did refers to, and we're going to use the service ID transformer. And the value of the service ID we're going to use is exam underscore SVC. So the Widley example and the transformer example are exactly equivalent, just a difference in notation. And they both resolve to that HTTPS URS example, colon whack-whack-example.com/endpoint, and then 8377464. The second example in the bottom half of that page goes a little bit farther and shows us a more complex example. So in the Widley line, it's the same did as before, and then semicolon exam underscore SVC /foo/bar question mark a equals 1 # flip. Well, using the did-uri-spec and the transformer notation, specifically for service IDs, we would say that the did $$ service ID equals exam underscore SVC, and then just the rest of the parameters. And so what happens is we think of that did being processed on the left of the exclamation mark, and it is replaced with the URL of the exam SVC in the did document, from the did document. And so both of the above URLs resolve or dereference to the example that we see at the bottom. So just a few notes. Did schemes and or did resolvers can define additional transformer options. They are not limited by the syntax specification. That's really key in terms of the open to innovation principle. The semicolon is no longer used or needed anywhere in the did syntax patterns across all the use case categories. And a related comment is that inside the did documents, we no longer need the semicolon. We can simply use # for everywhere, because the semantics comes from the transformer. So if you say $service ID equals foo, and foo has an associated service endpoint and service endpoint URL, then we just need a # within the did document. How we process that ID becomes a question of the query, and as we get into some slides that enumerate all the different kind of possibilities of inputs and outputs, that'll become more clear. Okay, so a lot of interesting background, a little bit of a little peek at how the did URL grammar works and what transformers are. So let's start, as we described in our approach, of looking at the actual use cases. So step one, we take the higher level did user scenarios, and these are the ones out of the did identifier use case document. These are the examples we see in the hypes. These are the examples we see in a variety of other documents. And from that, we perform our analysis and we deduce what we call did URL user scenarios. General patterns, not trying to enumerate every possible pattern or instance of a pattern. And once we have those high-level patterns, then we can generate the lower-level did URL use cases. So we go from higher-level did user scenarios to high-level did URL user scenarios. And then it's from there that we get the did URL use cases. It's not until we get these did URL use cases that we're able to really understand what the grammar is, the requirements against the grammar. And this is where the development of the grammar starts, although again, it's an iterative process. So let's look at each of those 3 steps in turn. So starting with the higher level did scenarios. So again, here's some of the documents that I've talked about before. The use cases for decentralized identifiers, the universal did operations white paper, the draft, feature discovery hype, the draft attachments hype. These are all sources of those high-level scenarios. From those high-level scenarios, did user scenarios, we're going to deduce the high-level did URL user scenarios. So here we've got about 19 currently. And so we see, for example, number 1, a did is going to resolve to a did document. That's simple. In number 2, we see the use of the select ID transformer. And for convenience, because we believe that did document fragments are probably going to resolve frequently or more frequently than anything else, we're also maintaining some backward compatibility with the # notation. Because we're continuing, it's not necessary, but one reason is we're continuing to use the # inside the did document. So, the did exclamation $select ID equals WXYZ, that gives us a fragment. Instead of using the select ID transformer, we could use the content ID transformer. In that case, we get a did document content fragment. Service ID, we've already talked about. There we don't get a did document and we don't get a fragment. We get a remapped service endpoint, URI or URL, depending on how service endpoints are defined. Often they'll be HTTP, sort of RESTful requests, or it could be a WS socket request. It could be whatever protocol that service endpoint understands. Attachments, we already talked about attachments. So this is being able to extract attachment ABCD out of an Indy 8-way agent-to-agent message. So this is a message attachment fragment. In the Indy feature discovery spec, there's the ability to query all of the service agent features or feature descriptions. So part of the JSON for the request object is the query attribute, and there you pass in the did URL that represents your query. So here we're saying for a particular did, we're going to pipe that through $filter this time. And the filter is star. It's a wildcard. So this says return everything to us. In number 7, we can see a similar construct, but when we look at the filter expression, it doesn't just say star. It says spec / tic-tac-toe / 1 dot star. So this is only going to give us the tic-tac-toe features. So we call this an array of filtered service agent feature descriptions. Number 8, if we pass in a did method like did : foo : or did : solve : and we pipe that into $service capabilities, we're going to get an array of did method capabilities, all of the did method capabilities. We might be interested for a particular resolver or for a particular did method, in this case did : XYZ : and simply getting all of the documents. And you might say, yeah, there could be hundreds of thousands or millions. there's other constructs that we'll see a little bit later when we get into the detailed low-level use cases for controlling how many documents are returned, which documents are returned, essentially a batching type capability. But the important thing here is we get an array of documents. So if you do just a quick scan down the right, every one of these returns a different result. In the first page here, we've got 9 different types of results from DIDs. We're solving the elephant problem. Here, the second and last page. Here we're going to take a DID and pipe it through, $exists. So this says, for this DID, find out if it exists. It doesn't say how. It doesn't say you have to reconstruct or deserialize a DID document to determine if it exists. This gets passed again to the parsing and processing pipeline, to the parser, the semantic analyzer, and the optimizer. And so the optimizer, in the case of Hyperledger Indy, might say, I just have to check if the NIM is there. If the NIM is there, then that's a shortcut I can use. In number 11, this is looking to see if a particular fragment exists. And we can go onwards from there. 12 through 16, everything that we've looked at before and everything we've discussed in the did-spec meetings and the did resolution meetings only deals with returning did documents, fragments of did documents, or remapped dids that are remapped using service IDs. But clearly this same notation could be used to return schemas, credential definitions, overlays, perhaps information about a node on the verified data registry. And so we see some examples here. The default, if type isn't specified, would be did-doc, and that would make all of this previous examples we've seen compatible. Stretching things a little bit, we can see $type might be config.pool to get the pool configuration document, or perfmon.pool to get the pool performance monitoring document back. Lastly, this is for a particular did method. We want to get the performance information of the performance counters for the did method performance monitoring document. Okay, so that's the middle level. Those are the high level did URL user scenarios. Let's go through a series of tables now to look at each of those categories in more detail. This is just a note that there's a bunch of different common did documents that are used as examples. There's example 16, which I believe is near the end of the did spec, perhaps an appendix. There's the Indy ARM, the Indy Hyperledger Indy Architecture Reference Model has a model did document that's referred to and available through the Indy browser. And then, of course, there's the Phil's article in the example that's there, and these link off These use case, category B, is the ones that use the semicolon. We don't use those anymore. It's been superseded by category H, which is what we used in the example, but we'll look at it again. Category C. So this is being able to do operations against a did doc. For example, test existence of a fragment. Did document collection operations. So here it's assumed that there's a collection of did documents and you want to return some or all of them or some subset. Use case 3, tests for existence of a single one, and that's the one that just returns true or false. Here, the next one is to determine if a particular fragment exists. 7 and 8 we've talked about a little bit already. These return the did documents, all the did documents available to a resolver, and 8 is all the did documents for a particular did method. But clearly those aren't practical. We don't actually want people to do that. In fact, there should probably be a default number of documents that's returned from the beginning of the collection. 9 is the proper way to do it. Return a batch of did documents available to the did resolver for a particular did method. And here it's using piping through get documents, but we're including additional operations like top and skip. So this says skip the first 100 did documents and take the top 10. So that would be 101 through 110. Those documents would be returned. Or we could pipe through get documents and use the filter expression. And then based on the filtered results, again, we could skip the first 100 of the filtered result and take the top 10. Lastly, in 13, this is just changing things up and changing them around. So we're going to take, we're going to skip the first 100 documents. We're going to take the next 10 documents, 101 to 110, and we're only going to return selected fragments from those did documents. So in category E, which is did resolver service operations, did resolver service operations, we've really reduced this down to at this point a single did URL use case, which is the ability to query the did methods that are supported on a particular resolver. F, did resolver service response format use case. So this is asking the did resolver to format the response in a particular way. So there's a URL for a specific did document, and we're going to return it as JSON, as Atom, or as XML, and JSON being the default. Did resolution decode decrypt use cases. These I'm less familiar with, but there has been discussions saying that either parameters have to be supplied to decode a did document, decrypt a did document, or perhaps encode or encrypt a did document. So these are kind of notational examples, syntactic examples that need to be clarified. H, this is the service endpoint transformer option that we've talked about before in our first example. I, this is did service endpoint dereferencing. So this is an example where we're not trying to get a transformed URL for the service endpoint. We're simply trying to get the JSON fragment for that service endpoint. And there's the two examples. Here's the two use cases for the rest of J. Previously we saw what it currently looks like, but if we go down to the query in use case 18, we can see that we take the same URL as in the type statement, and we pipe it through exclamation filter equals and then spec tic-tac-toe 1 dot star. So that would be equivalent, exactly equivalent to the one before. In addition, just to highlight this example, we want to return all of the features that are supported. So here we're piping it through $filter equals star. So here we're going to enumerate the capabilities supported by a particular method. This was the one that was deferred from above. So for a particular method, did :xyz, pipe it through $supported capabilities. You'd get a document back that describes all the capabilities of that did method on this particular resolver.
Category L allows us or extends the did URL specification to enable the retrieval of different document types from the verifiable data registry. Not just did documents, but schema documents, credential definitions, the whole overlay framework, information about the nodes, the node document, and then use case 25 is type any, and that's similar to any in the DNS query protocol, where you want to be able to retrieve many different types of documents. And all of these would probably be mitigated either with $filter, $top, $first, etc., to control the volume or the batching of documents that are returned. On this slide, we see one of the first drafts of the did-uri-spec grammar. It greatly simplifies the grammar relative to the previous quote did ABNF grammars. In the center part of the grammar, where you see the transform equals pipe, followed by at least one transformer separated by ampersands, and that a transformer is either just a name like $exists, or it's a name value like select ID equals, double quote, exam underscore SVC, and the rest follows out pretty simply. So it's elegant, it's almost cute, and greatly simplifies the grammar for did URIs.
Tooling. Just a couple slides here. So a parse is the name of the automatic parser generator, and it's at parse2.com. It automatically produces a parser generator based on the ABNF grammar you pass to it, producing Java, C++, or C# code. And so this will be used to create the reference parser for the did URL spec that can then be reused across all of those projects, all of those high-level user scenarios that we talked about. Here's a testing tool we're using, which is BNF Parser 2. In the bottom left, you choose the file, the ABNF. The symbol to choose is did URL. Did URL is always really the topmost component in the grammar. And there we're testing just did :xyz :1234, and it would give us the result. Some of the implications, so the impact on the document grammar is that semicolon is no longer needed anywhere. From a syntactical perspective, all anchors or selection IDs, whatever you want to call them, they can be prefixed by #. We don't need to have different symbols for different kinds of fragments or different kinds of processing, and that the semantic meaning is determined by the referring did URL transformer. So if it's $service ID, it means that we're going to treat that anchor, that selection ID, as a service ID, service endpoint ID. If it's select ID, we're just trying to get a fragment, etc., etc. Impact on other specifications. So as we use these other specifications to learn more and more about the lower level did URL use cases, there's potentially a reverse impact, for example, that semicolon business, where we come back to those projects and say, well, here's the did URL spec. You're going to have to tweak your implementation to conform. So here's an example of a did document. This is the example 16 of the did spec. And we can see the only change here is really that the semicolon is changed to a pound sign. And all the constructions above would work. So wrapping up, the next step is to grow and validate the number of higher level did user scenarios, and more specifically, create more lower level did URL use cases. And we want to engage more diverse, did user communities, more diverse higher level did user scenarios, get into more of the hypes, look at other did platforms like IPID, etc. We've been taking a very methodological approach to building the grammar, and at this point we don't have a grammar. What we've been focusing on is following our process and building the use cases. So one of the very next things is to actually build out the grammar itself. And kind of related to the first bullet, continue to grow the outreach, awareness, knowledge, and understanding of the did URL spec amongst diverse did communities, and documents and specifications that represent these higher level did user scenarios. So if you have any questions, my name is Michael Herman. I'm an independent blockchain architect, and there's my email address, mwherman@parallelspace.net. I really have to thank you for hanging in there for the last 75 minutes, and I really look forward to receiving your feedback. Thank you.